Hello everyone, I am Mara de Joannon, and in the next 35 minutes we will talk about the other side of combustion, shifting from traditional flame that you see at your left to the system where no visible flame is present, that is at your right. This is why I put a moving video in order to make you sure that something is happening in the video I am showing you. And of course there is a totally change, a drastic change in the paradigm we are used to. Because this symposium aim to emphasize energy transition, I would spend a couple of words talking about energy, looking at needs and critical issues that we have to face for transition, and what is the role that the combustion process has to cover during and beyond the transition, and how we can frame the role of mild combustion, looking at its feature structure that we can see in the volume, fuel flexibility in terms of kinetic and pollutants, and the related research needs and challenge. I'm saying nothing new, underline that there are two main enabling concepts for energy transition. That is the utilization of renewable that has to be maximized, and the electrification of energy grid that often is thought is as the highway for the exploitment of renewable energy source. And in this panorama about the shared installed capacity of a renewable energy source, we have to face with a very huge number that have to be phased in the very next year, because the installed capacity is considered to be increase of about 180-90%, with a shared capacity of that has to reach 77%. To face with such a huge amount of installed capacity, we have to face with two main issues that are availability of critical metals and infrastructure. Why critical metals? Because they are key enablers of renewable energy source, and when we look at needs of metal for energy transition, the number shows that the global mineral reserve needed to meet the target of energy transition do not cover the needs. And it is even worse if we look at the capacity to mine the metals due to technological limitation of mining. Of course, the requirement could be satisfied with the end-of-life recycle, but we should need of this rate of end-of-cycle recycle in order to meet the energy transition goal, but the actual rate is like this. Thus, the critical mineral shortage could disrupt the global supply chain. Of course, there are other drawbacks that comes with massive utilization of critical metals. That are the impact that the massive extraction of metals has on the environment in terms of disruption of mining regions, and the huge amount of pollution of the land, water, and air that cause a really severe environmental damage. There is a second critical point related to the environmental impact of critical metals, that is the exploitation of unexplored region for mining of critical metals. This is the case of, for example, of deep sea, that is the sea deeper than 200 meters, that has abundant level of metals such as copper, cobalt, nickel in different geological aggregates, and it is estimated that the sea has cobalt, for example, about 6 times as much as the current land-based reserve, and a reserve that correspond to $16 trillion. The race of deep sea mining is already started, but unfortunately the mining of all these materials has an unforeseeable and unavoidable impact over the ocean and over areas and ecosystems that are still unknown. Indeed, Cutting and dragging of rocks generate localized plumes and solid waste material deposit, and that also contain heavy metals, so they are toxic and then can affect also the fish resource. And another point of pollution is noise pollution that will impact on whales and also on other marine life. The other issue we have to face with during energy transition is the availability of infrastructure, and we have to keep in mind that for not industrial application, just to look at people with no access to electricity is about 10% of world population. That is almost equivalent to European population or 3 times of US population. Of course, the same problem with infrastructure is also relevant for industries, but the other point of industries is there are many sectors that are to electrify because of temperature, for example, involved in process. This is the case of material industries, or because of obvious consideration related to aviation and heavy duty transport. Of course, in this framework, combustion has to be thought and becomes a key enabler of renewable, covering a fundamental role and support of renewable deployment. Indeed, the combustion helps to maximize the use of renewable, taking advantage from the chemical storage that is by far the most efficient way to store energy in terms of duration and capacity. The net income is that following that path we have a very wide palette of molecules from low calorific value as biogas and ammonia to alcohol, biomethane and hydrogen, and then these are only a few examples that have very different characteristics in terms of combustion intensity, so very different heating value, flammability limits and laminar flame speed. So what is the point? Is that we need an ideal combustion system that should go beyond these characteristics and should meet the criteria of flexibility, both in terms of fuel, to easily allow the fuel switching based on locally and timely available energy carrier, and also in terms of operational condition in order to meet the characteristics of the process, so in terms of composition and of load, of temperature and so on. So coming back to the other side of combustion, mild combustion is one of combustion process that meet this criteria of flexibility. So what about mild combustion? It evolved from a very highly preheated reactant, preheated at temperature higher than their ignition temperature, and very diluted reactant, diluted at composition that fall outside the flammability limit. So they are so diluted that their temperature increase during combustion is lower than ignition temperature. So, looking at a map where oxygen amoral fraction and local temperature are reported, of course, this region is related, the upper left region is related to the standard combustion process, so with the composition higher, with oxygen amoral fraction higher than flammability limits, so is associated with the stabilization of a flame front and high temperature increase, and mild combustion is indeed placed in this region where we have different kind of process. Of course, it is really clear that lowering the oxygen concentration and corresponding to high recirculation rate, there is a strongly decrease of Dunkeler number. So fluid dynamic and chemical time scale become comparable. If we set together all the keywords we talk about, I mean low temperature, dilution, preheating, recirculation, we have altogether a process that lead to a process with inherent feature. Indeed, it is flameless. No flame structure are visible in the visible range. It is noiseless. It is characterized by a uniform, quite almost uniform temperature concentration profile. It is intrinsic shelf-stable because it's evolved from ignition temperature. It is based on ignition. It is pollutantless. And indeed, if you look at the range, temperature and composition range related to the main pathway of pollutant formation, we see that mild combustion fall outside the range of, for example, thermal NOx, that is the main pathway for NOx formation, and for sure outside the range of soot formation. So let's go to analyze the flexibility of a mild combustion. Mild combustion was proven to be a robust combustion system for fossil fuels. So let's explore the flexibility of mild combustion, looking at those carriers that are archetypal for the energy transition, I mean hydrogen and ammonia. That also, with respect to the characteristic of fossil fuel, they move towards opposite direction. So H2 with high combustion intensity and NH3 toward low combustion intensity. As initial consideration, starting from the definition of mild combustion, we can see that looking at the temperature ratio for these three fuels, ammonia, methane and hydrogen in air, we can see that increasing the local dilution and looking at the range where mild combustion occur, ammonia has reached earlier at lower dilution mild combustion in condition, instead of hydrogen that will reach mild combustion in at higher dilution level. This is of course related to their characteristics as fuel, and so higher combustion intensity for hydrogen and lower combustion intensity for ammonia. That, of course, in this case, here are mainly related to heating value of different kind of fuel. How to reach, from a practical point of view, the local dilution and preheating needed for reaching mild combustion? In general, there are two main configurations that are taken into account. The reverse flow, where a confined burner is considered, and in this case, a large part of fuel is abandoned and returned towards the inner region. And in some cases, and let's say in most cases, the outlet is on the same side of the inlet section. And this is the example that are at laboratory or pilot scale available in the many research centers all over the world, from Portugal to Australia to Germany and to Brussels. The second configuration refers to a cyclonic flow that is mainly considered as whirling motion fluids that move around a central axis, characterized by a spiral pattern mainly determined by injector orientation and vessel geometry. And also in this case there are many examples at laboratory pilot scale in all over the world in groups that works on mild combustion. As already told, we have a change in paradigm of ratio between fluid dynamic and chemical time scale. Indeed, generally, traditional combustion process are characterized by the fast chemistry hypothesis because they are characterized by chemical times as very low with respect to physical time scale. In case of mild combustion, the time scale of fluids dynamic is comparable to one of chemical time scale, because as already stated, it evolves around with a very low Dunkellier number. Let's go to see how this impacts on characteristics of mild combustion. We saw that it is a process that is considered homogeneous at macroscopic length scale of the combustion chamber, because it is characterized by nearly homogeneous temperature concentration profile on macro scale. but it is inhomogeneous at a smaller length scale, as demonstrated by optical diagnostics applied to the combustion chamber working in mild condition, and results shown in the figure. And so on the macro scale there are evidence of a patchy appearance of a spontaneous igniting kernel that ignites, grows, and then disappear. Authors also in direct numerical simulation studies evidence this distributed zone with different shape that they defined, identified based on their form and shapes as blobs, pancakes, and ribbons that are single or interconnected, and mainly based on ignidiffusion. Ignition is a specific spontaneous ignition process that, at dissipative scale, differently from autoignition, that is an homogeneous process, consider, in addition to generation term, also the diffusion process, that in this case matter. An extensive characterization has been made in literature of ignidiffusion, and looking at the evolution of a process and the stabilization of a structure in a mixing layer derived from the interaction of hot and diluted stream of fuel and oxidant. In particular, looking at the shapes of heat release rate in the mixture fraction domain. The comparison between undiluted and diluted heat release rate profile obtained for methane impinging toward a hot jet of oxidant show that the ignition profile related to diluted condition show no pyrolysis region, show no correlation of stoichiometry and maximum of heat release location. Moreover, it showed the absence of stratification of a reaction product in the mixing layer, and in addition a widening of heat release region. Following the trend of ratio of zeta max over stoichiometric mixture fraction as function of fuel dilution, we see that at a certain fuel dilution it experiences a very steep decrease that corresponds to a very steep increase of standard deviation. At the same time, if you look at Dunkeler number, also Dunkeler number experience the same step decrease as the other two quantities. So this where the region where the step decrease of the Dunkeler number occur can be identified as the region where ignition occur. This was happened for methane, but the same characteristics are kept from ignifusion structure of ammonia and hydrogen. Indeed, looking at heat release profile of hydrogen with in increasing of dilution, we can see that also in this case the stoichiometric mix factor is correlated with maximum heat release until a certain value of dilution where this uncorrelation occur. At the same time also the profile widen as in the case of methane, and this occurs also in the case of ammonia. So looking at the value of the Dunkeler number with respect to the fuel dilution, the same trend of methane is obtained. So independent of the carrier, it is possible to identify a dilution range where ignifusion occurs with analogous characteristics. But of course, as we already stated, there are different range of dilution where the mild combustion, or in this case ignifusion, occur because ammonia reach ignifusion condition at lower fuel dilution instead of hydrogen that has profile related to ignifusion at higher dilution level. With a cooling number so low, the kinetics is very relevant and it helps to identify some invariant key parameters for stabilization of mild combustion, such as a characteristic temperature. If you follow the ignition of system over the time, here there is a qualitative diagram. In the range of interest, the temperature evolve following this kind of trend. Starting from an initial temperature, it reaches the ignition temperature defined with the proper criteria through the intermediate temperature branching reaction system, and then the temperature increase toward the adiabatic temperature. In case of appropriate inlet initial condition, the system evolved directly through explosion through the adiabatic temperature through the high temperature branching of hydrogen system. So if you look at temperature, increase of temperature that we reach after the ignition as function of ignition temperature, we see that if this is the value obtained for air, increasing the dilution, this value of course decrease as temperature of ignition increase up to reach a certain value where the two value, the temperature increase and the ignition temperature coincide. So the ratio that we have identified as mild combustion region is equal to 1. Since this starting point, the further dilution increase make the system work in let's say mild combustion condition. What's happened if I consider the temperature at which the explosion occur? We can see that these two temperatures, the one related to ignition, one related to explosion, are different until a certain value of dilution. After that, they almost coincide. This is a signature that at high dilution level, the process evolves through the high temperature branching of hydrogen system. Indeed, if you look at the ratio, if we follow the ratio between high temperature branching and the intermediate temperature branching of hydrogen system in case of methane ignition, we see that in case of air, so no dilution, this is the trend of this ratio, and it is always lower than 1 until the very high temperature. What happened with dilution? Dilution make this ratio shift toward higher value until to reach some value of dilution where the ratio is always higher than 1, and this defines that the process evolves through the high temperature branching. The same situation, the same discussion can be done for the other carriers, methane and ammonia, because starting from the low temperature branching, high temperature branching characteristics of hydrogen, they also sustain, of course, the low temperature oxidation of methane and low temperature oxidation of ammonia, and at the same time the high temperature oxidation of methane and the high temperature oxidation of ammonia. And this the temperature that highlight, that sign the passage between one controlling mechanism and to the high temperature controlling mechanism is very critical for stabilization of mild combustion. Indeed, this temperature delimits the range where mild combustion can occur, representing the minimum temperature at which mild combustion can be stabilized. And this is almost independent on the fuel considered, for as it is shown in this figure, where H2, alcohol, and methane, and also other propane and other carbon-based fuel are characterized by the same minimum temperature for mild combustion stabilization. The difference is highlighted for ammonia that always rely on this kind of branching mechanism, but it is modulated by chemistry related to nitrogen containing species. These invariant temperatures have been identified experimentally in the cyclonic burner we used to widely characterize mild combustion for many energy carriers. Looking at methane, pyrogas, alcohols, and ammonia, we found this invariant temperature. And what we see also in this figure is that we were able to stabilize process also outside the flammability limits. This is quite obvious because a mild combustion process rely on autoignition and not on flame propagation. It is also interesting to see how the mixture of carriers behaves in respect to the minimum stabilization temperature of mild combustion. So it is interesting to look at results obtained from the study of mixture with ammonia, and we see that if the minimum temperature of this carrier lie in this region, so between the temperature highlighted in the previous discussion, and ammonia instead is in this region, the minimum temperature of the mixer lie in this on this line, and they delimit the region where the stable operation can be found for this kind of system. In case of hydrogen, also it is possible to identify a minimum value of the temperature for which it's possible to stabilize a mild condition for its mixture with ammonia, but we are not able to consider 100% of hydrogen in this condition. So in principle, you have not identified hydrogen minimum temperature for mild combustion stabilization in cyclonic burner, but in literature, a numerical study supported by experimental evidence identify as minimum temperature for hydrogen stabilization of mild combustion in same range that we have identified for other fuels. So the dilution highlighted a very high critical role of third body species. Indeed, the dilution makes the reaction evolve in presence of higher amount of, for example, CO2 and water, than in standard combustion case have a very high third body efficiency with respect to other species, and therefore its evaluation become very critical. Indeed, it assumes very high values in different that are also very different, passing from one chemical mechanism to another. But the key point also to be underlined that new molecules can be considered as relevant at the same level of water, for example, has a third body in chemical kinetics. This is the case, for example, of ammonia, that is more polar than water. Then that has been demonstrated that heat act as a third body species in many reactions with very high efficiency as third body. But ammonia is not the only carrier that can be considered and that has to take into account as a third body when we look at kinetic mechanism of this new carrier, because also alcohol, for example, can have the same characteristics, but no information in literature are present yet. And the formation of pollutants in case of this new carrier that we are considering, in case of their utilization in mild combustion. We already saw that as a starting point that thermal NOx are not favored in case of carrier like hydrogen, methane, and carbon-based fuel. But what happens so in case of ammonia? Also in case of ammonia we have limited amount of NOx formation during the mild combustion process. To understand this point, let's give a look to ammonia combustion kinetics. We know that the first relevant step is that ammonia dehydrogenate to NH2 that at low temperature lead formation of NO through the formation of H2NO species or directly. In same temperature range, the NOx chemistry is also active, consuming the NO present, possibly passing through the formation of NH. At higher temperature, NH2 dehydrogenate again, leading to the N2 formation and destruction at temperature higher than 1400 K. At higher temperature, the thermal NO is formed, and also the recombination of NH2 occur at higher concentration of fuel. So what is the point? Is that mild combustion is active, is stabilized in the temperature range where thermal NOx are not formed, the channel is not active, and the NOx chemistry is active. What is interesting to know is that when we look at a mixture between this carrier, I mean methane, alcohols, hydrogen with ammonia, the situation worse because the presence of methane, hydrogen, and alcohol increase the concentration of OH that limit the NOx channel that is responsible of a destruction of NO formation during mild combustion. A key relevant strategy that can be used thanks to the characteristics of mild combustion is the use of water for reduction of NOx, further reduction of NOx emission. Of course, this strategy has been proven from experimental point of view in the cyclonic burner, but it is also demonstrated from numerical point of view, considering a jet in hot co-flow configuration. As already stated, the condition we look at are local conditions when we look at when we discuss about mild combustion. I mean, in terms of dilution and preheating. This means that mild combustion can evolve from fresh air and undiluted fuel. This, of course, means that the heat exchange is a key, relevant point for stabilization of this kind of process. Indeed, starting from fresh air and undiluted fuel, it is needed to exchange the right amount of heat in order to reach the condition of mild combustion. So, looking at the carrier that we have identified, hydrogen, ammonia, and methane for comparison, and having identified the minimum temperature that we have to reach inside the combustion chamber in order to stabilize ammonia, hydrogen, and methane combustion, it is easy to identify the region of heat exchange where we can stabilize the process. And the limit of this range corresponds, of course, to the minimum temperature that we need for mild combustion stabilization and the maximum temperature that characterize mild combustion process. It is worth to note that data collected in cyclonic burner using these three carrier falls in the range identified on the diagram. The radiative heat transfer in mild combustion is much relevant with respect to the other combustion process. This is widely demonstrated in literature, and this is a key point when we are looking at new carrier as hydrogen. Indeed, fixing the power for a specific system, if we use hydrogen instead of, for example, methane, we have a lower concentration of emitters in the reacting volume. But in literature has been demonstrated that overall the net heat flux increase using hydrogen because of local higher temperature that are reached during hydrogen combustion. Nevertheless, if there is the need of increase of radiative heat transfer, it is possible to use the strategy of adding emitters like water in the combustion volume, because this does not alter the stability and the characteristic of the process. So what about application? In the hard-to-abate sector, the mild combustion is one of the main combustion process that is used in this energy transition. Indeed, it is a very high maturity level with system that spans from 100 of kilowatt to megawatt. And of course, we refer to, in this case, to material industries that, as you can see from the figures, the range of processes fall in the temperature range characteristics of mild combustion. What about a process that works at high pressure? They are still at laboratory scale analysis because of some issue related to stabilization of mild combustion in case of high pressure. Indeed, at high pressure the Dunkeler increase, and so as it is expected the mild combustion region appear narrower with respect to the process evolving at atmospheric pressure. At the same time, however, there will be a beneficial effect of pressure in reduction of NOx emission. There are some systems, laboratory scale, that have been set on for the study of high pressure mild combustion. This is the case of jet nautical flow present at the University of Adelaide, or inter-turbine burner of Delft University that rely on a cyclonic configuration, and the lean azimuthal flame University of Cambridge that works in some region, in some condition, in mild regime. And also the flux high pressure burner that is at DLR it has been tested several times. Some results have been reported by a hacking group that worked on a reverse flow configuration where mild combustion have been stabilized for methane or pre-vaporized liquid fuel, and mild combustion has been studied at 1 and 5 bar. And they showed that keeping the velocity, increasing the pressure, they are able to keep the same level of NOx emission. Thus, no systematic studies are present in literature about mild combustion type pressure. And in our lab, we have set on a high pressure facility based on cyclonic flow, so high pressure cyclonic burner, with a new internal fluid dynamic configuration that is bio-inspired in order to maximize the fluid dynamic condition and exchange inside the reactor. It just started and it will be used for a wide campaign for characterization of different energy carriers from hydrogen to ammonia to sustainable aviation fuel at high pressure. Of course, this study will be supported by the results coming from other facilities like data coming from jet zero reactor working at high temperature. It has been already set on in our labs, and the optical diagnostics characterization that will come from a scaled down cyclonic burner that started to work in the last days. So the main conclusion that we can state is that mild combustion works is really fuel flexible, but there are many challenges that we have to face with. First of all, we need of a comprehensive understanding of local length and time scale that needs to understand and to have an effective modeling paradigms in relation to a full description of mild combustion process. Moreover, it's needed the enlargement of a range of investigation, for example, as already stated, in terms of pressure. And it is also interesting to have the identification and to work on identification of a new paradigmatic fluid dynamic configuration in order to optimize such configuration in relation to the process that we need to face with. It is also needed to extend the study of flexibility to other carriers with very particular characteristics such as sludge or also raw bio oils. And in this context, it is also interesting and project active on the utilization of mild combustion in more extreme conditions in terms of fuel oxygen ratio, and in order to make it work as a reformer for syngas production. The coupling with other technology can be a further strategy to extend the range of stability and the use of mild combustion with fuels or pyrogases or biogases with even lower heating value. This is the case, for example, already explored the possibility of coupling of system mild combustion with a solar assisted unit that has been pursued by University of Adelaide, and or to think to couple mild combustion with plasma system has been numerically evaluated from our group and group of Professor Mardani in Iran. Finally, I will thank you all people that belongs to my group, because everyone contributed in different way to this presentation.